All right, so in the previous example from the end of our last video, we described a function that transformed vectors in R2 to other vectors in R2 by rotating them 90 degrees. And then we said, assuming that function can be given as a linear transformation, meaning we can have a matrix that that defines that linear transformation, we want to define that transformation, that matrix, and we did that here. Okay, I want to do a similar example with a different type of transformation. So here, let's suppose that we have a linear transformation T of B, which maps R2 into R2 again. And let's suppose this linear transformation doesn't rotate vectors, it just scales them by a factor of 2. So in other words, it doubles their size or doubles their norm. Okay. Once again, we're going to assume that this is a linear transformation, which it is, so that's a valid thing to assume here. We want to find the matrix B that would do this. So same idea, I want to take a look at my standard basis vectors. I and J, and I simply want to double their size. So under this transformation T of B, let's call this 1 and 1. J is going to double in size but not rotate, so this becomes TB of J. And same thing is going to happen with my vector I. It's going to double TB of I. So this would be 2 here and 2 here. What does that look like when we find the image of these vectors in component form? Well, TB of I doubles the length of I. So instead of 1, 0, I have 2, 0. TB of J is going to double the length of J. So instead of 0, 1, I have 0, 2. That means my matrix B is 2, 0, 0, 2. And again, what does that do? Well, that now using that as a linear transformation, if I want to scale any vector by a factor of 2, I can just multiply it by this matrix. Now, you can already scale vectors using scalar multiplication. So basically what this shows is multiplying a vector by a scalar 2 is the same thing as multiplying, as long as the vector is in 2 space, multiplying it on the left by this diagonal matrix. It accomplishes the same thing. All right, now those are two simple transformations, but what if we wanted to do a transformation that combined them? So let's suppose that we have a function that does two things to a vector. You take an input vector and you first begin by rotating it by a 90-degree counterclockwise turn, and then you scale it by a factor of 2. Well, you could do the same thing that we did in the previous two examples. You can take I and J and first rotate them 90 degrees and then scale them by a factor of 2 and then use that to figure out what the component forms would look like. Or you could just think of this as a sequence or a composition of two functions and use the work that we already did. So if I have a vector x and I map it to the vector TA of x, what does that do to x? Well, this rotates x 90 degrees. That's the job that this function has, is rotating vectors by 90 degrees. And then I'm supposed to take the result of this and scale that by a factor of 2. So that output vector is now going to be used as an input vector for this second transformation. That means I plug that into my T of B transformation. And this scales not x, but TA of x, the image of x under the first transformation, by a factor of 2. Okay, So whatever the image of this composition of functions is, represents what we would get by first rotating x by 90 degrees and then scaling it by a factor of 2. But let's think about what this would look like. If I have the linear transformation TB of TA of x, by definition, TA of x is just a times x, right? But then if I were to take this and use it as an input for this function, this would be b times its input, b times a x. Use my arrow notation. And then finally, that's matrix multiplication, which has the associative property. I could write this as BA of x, which is what we were asked to show. Now, how is that useful? Well, if I were to actually multiply the matrices B times A, then I would have another 2 by 2 matrix, and that 2 by 2 matrix can be used to accomplish both of these transformations at once in that sequence. Rotate by 90 degrees and then scale by a factor of 2. Really, really useful, because what that does is it kind of gives real meaning to matrix multiplication. Again, matrix multiplication is defined initially in sort of a bizarre way. It seems like a random way to define how two matrices should be multiplied. But what this reveals is that a product of two matrices is in fact the same thing as function composition. It's a composition of two linear transformations. And again, all of these ideas we explore in more generality in chapter 8. But this should hopefully give you somewhat of a visual to work with, which can help when we get to that point. Okay? All right. Still focusing on linear transformations in R2, or mapping R2 into R2, I want to do a geometric characterization of a linear transformation. So there's two important things to bear in mind when we talk about linear transformations. First of all, for any 2 by 2 matrix, and again, this generalizes to any linear transformation, but we're just thinking about R2 into R2 for now, the 0 vector will always map to the 0 vector. Okay, so the 0 vector is never stretched or rotated anywhere else. And that kind of makes sense because you can't take a point and stretch it into a vector. And if you rotate a point, nothing changes about that point. So we would expect that. Secondly, the image of a line in R2 under our linear transformation is also a line in R2. Remember, a line is an infinite set of points, and we talked about how if you have a region, or in this case a curve or a line, and you plug every point in that line, thought of as a position vector, into your linear transformation, then the result should be another set of points which we can think of as the image of that original curve or line or region or whatever it was. So what this is saying is that linear transformations don't mess with lines in the sense of turning them into something else. Some functions do. Other functions that are not linear transformations may take a line and bend it into a parabola when you look at its image, or a circle, or some other kind of curve. But linear transformations only ever take lines to other lines. These are both straightforward to prove. For example, if I wanted to show that the image of 0 is always 0, then I plug the 0 vector into my linear transformation, which is the same thing as a times 0. But regardless of what a looks like, when we multiply it to the 0 vector, we end up with the 0 vector. That's it for that first part. Next up, we're going to use what we did in chapter 3, where we came up with the vector equation for a line. So here, let's let L be any line, and to give some character to that line, let's say that it's parallel to some vector v, and it contains the point with position vector x naught. Knowing these two things allows me to come up with the vector equation for this line, which we talked about in chapter 3. X equals x naught plus tv for some scalar v. So if you look at any point on the line L, and then so any point that has position vector x, and then plug that into your linear transformation. Remember, x can be expressed this way for some scalar t, and then our linear transformation we showed takes linear combinations of vectors. This is a linear combination of the vectors x naught and v, and maps them to linear combinations of the images of these vectors, ta of x naught, ta of v, where the coefficients on that x naught and that v are kept the same, 1 and t here, lowercase t. But what is this? Well, this is the equation of a line that has the point with position vector ta of x naught and is parallel to the vector ta of v. So basically, if we want to plug an entire line into a linear transformation and see what the image looks like, all we really need to do is transform one point on that line and then transform this vector that the line is parallel to, and then we'll get the new line with just that information. Okay? I'm going to give you a visual to see what this looks like, but first we're going to do an example here. Okay? So in this one, I have this linear transformation, t of a, where a is given by this matrix, 1, -2, 1, 4. And remember, when we're looking at a linear transformation from 2 space into 2 space, we think of the columns of this matrix here as being the transformation of your standard basis vectors. So in other words, the vector I gets mapped to the vector 1, 1. Okay, so that guy right there. The vector j gets mapped to the vector -2, 4. So -2, 4 is up here. Whoops. Okay. So notice it didn't just ask me to transform the standard basis vectors I and j. It wanted the images of the coordinate axes under this new transformation. So how do I do that from what I just came up with? Well, the x-axis can be thought of as the line containing all scalar multiples of the vector I. Hopefully you can see why that's the case. If I multiply I by any positive scalar, I get some vector on the positive x-axis. If I multiply it by a negative scalar, I get some vector pointing in the direction of the negative x-axis. Multiply it by 0, I get the origin. So what this tells me is that the line that was parallel to I is going to be transformed into the line that's now parallel to the image of I. So that's going to give me this line right here, which I'm not drawing terribly well, but you should get the idea. Okay, so my x-axis, when plugged into this transformation, is going to get mapped over here. Same thing's going to happen here. The image of j is going to correspond, j, if I take any linear any scalar multiple of j, that's going to determine this y-axis. And so the image of the y-axis under my transformation is going to be the line that contains this vector right here. So be careful about how I draw it. It's going to look kind of like that. Okay. Now what this basically does is it creates a brand new coordinate system. And we're going to explore that much more in chapter 4. But it's taken my standard basis vectors and turned them into a different set of what we also call basis vectors, and those determine a new coordinate system. So rather than measure the coordinates of points using x and y, which corresponds to this horizontal and vertical axis, I treat these new lines as a different set of axes, and I can measure coordinates of points relative to that. We're not going to do any of that right now, but we will talk about that more in chapter 4. So it's sort of a preview of that material. Okay? So an important consequence of the definition of linear transformation and the properties we just talked about, not only, we're not going to prove this, but not only do lines get mapped to other lines, but if you map several parallel lines in R2 to their corresponding lines in a under some linear transformation T of A, then those images will also be parallel. And not only that, they'll be, if the original set of lines was equally spaced, then the images will also be equally spaced. So basically, here's an example where the vectors I and j, if this is I right here, and this is j, if you have a linear transformation that maps j to this vector right here, so think of that as ta of j, and maybe leaves I alone, so this is also ta of I, then that would map the y-axis to this line and the x-axis to itself, so the x-axis doesn't change. But then if you were to go a little bit further with your coordinate system, if you took your Cartesian plane and represented it as a grid of horizontal and vertical lines, as we oftentimes do, then the transformation of all of those grid lines will be skewed in the same way that your axes, your x and y axes were, and it essentially creates a new grid. By including that entire grid like that, essentially what we're doing is looking at how a linear transformation actually transforms the entire plane, how the effect of that transformation squishes or rotates or skews space in different directions. Okay, so this type of transformation here is called a shear. A shear is when you keep one of your standard basis vectors parallel to the or the image of one of your standard basis vectors parallel to what it originally was, but then you map the other standard basis vector to something that's not parallel to what it originally was, and it causes this sort of, you know, pushing of space in a particular direction. It gives it this sort of squished effect. Okay, all right. Where this gets kind of interesting is when we look at entire regions in space and look at what the linear transformations will do to that particular region. So notice here I have R2, this is 2 space, and this is very small and faint. It might be hard to see in the video, but the intervals on these axes are counting by 1, so 1, 2, and so on. So this is a unit square right here, and I've shaded it in. It's got all the points in its interior included. What would happen if I plugged in this entire region into a linear transformation T of A that does this to those grid lines? Well, it's going to take that square and squish it into this parallelogram here, okay? And it will do that for any other region as well. If I wanted to take a circle, you know, I'm not going to draw it here because we're going to do an example like this later, but if I wanted to take a circle and represent it, you know, somewhere in my two-dimensional space, and then plug that circle into my linear transformation, it's going to squish it the same way that this square was squished into that parallelogram. Okay? Where this gets interesting, I think, is when you start to look at the area of regions here compared to the area of their transformed versions. And that is where we get a geometric interpretation for our determinant. So that's what we're going to talk about next. Okay? So, I mentioned back in chapter 2, I believe that when we define the determinant, kind of like matrix multiplication, it seems like a bizarre, random way to define an operation on a matrix. However, the definition that we gave ended up with a lot of useful properties. We were able to show that if the determinant of a matrix is non-zero, then we have an invertible matrix, and if it is 0, we have a singular matrix. That's an interesting interpretation of that. The determinant shows up in Cramer's rule, which we didn't cover, but it's a way of solving linear systems. It's got lots of uses, but it's still difficult to see what it really represents. And now, with the work that we've done on linear transformations, we can see a more direct application of at least a 2x2 determinant geometrically. So let's suppose we have two vectors, v and w, and these are vectors in 2 space. If we put those two vectors in a position that gives them the same initial point, then we can we can copy V up here, copy W over here, and now what we have is a parallelogram. We've seen this parallelogram before when we defined the sum of the vectors W and V. It turns out that the area of this parallelogram can be found using a determinant. But how? Well, if I wanted to calculate the area of this parallelogram, I first need to know the components of V and W. And notice here I say V has components A and B, W has components C and D. So you can see from the diagram where the A's and the B's, the C's and the D's would show up relative to the components of W. And you notice there's a lot of symmetry here. These green triangles should have the same area. These yellow rectangles should have the same area. These purple triangles should have the same area by all of the symmetry going on here. I can calculate the area of this parallelogram by simply taking the area of this rectangle and then subtracting the area of all of these non-parallelogram pieces, each of which has an easy area formula to calculate. So first of all, what is the area of the larger rectangle? Well, its dimensions are A plus C by B plus D. So A plus C times B plus D is going to give me the area of the larger rectangle. Now if I want to subtract away these other areas, notice the area of either of these yellow triangles is BC, so I can subtract 2BC to get rid of both at the same time. These are triangles, but notice if I took this triangle and set it on top of this one, it would form a rectangle that has an area of A times B, so I can subtract A times B, and that takes care of both triangles at once. Similarly, I can subtract the two green triangles by simply subtracting C times D. Okay. Now if I expand this first part here and then do a lot of cancellation, look at what's left. AD minus BC. That looks a lot like a determinant. That's equal to the determinant of this matrix here, ACBD. It might be a little weird seeing the C here and the B here, but if I switched the B and the C, I would still have this determinant because it's just a transpose of this matrix. The determinants should be equal. I'm putting it in this order for a specific reason. The reason for that is because if you look at this matrix, AB is exactly the components of my vector V, and CD is the components of my vector W. So what that's showing is that at least in this case up here, if I take my vector V and if I take my vector W and form a matrix by making them columns of that matrix, V first followed by W, then the determinant of that matrix will give me the area of this parallelogram. Interesting, right? However, we need to be careful with that because we have seen already that a determinant does not necessarily come out positive. A determinant can come out to a negative number. It can also come out to 0. How do we interpret that in this area interpretation? Well, first of all, we're not going to show this here, but you can show that the only reason this determinant comes out positive is because of the order that I put these columns in. Remember, this corresponds to the vector V, my first column. Second column corresponds to W. If you look at the vector in your first column geometrically, and if you have to rotate counterclockwise to get to the vector from your second column, that will always give you a positive determinant. If I reversed the columns in this matrix, if I put W first and V second, we know from our work in chapter 2 that interchanging any two columns of a matrix will give you the opposite of the determinant that you would have gotten otherwise. So interchanging W and V, putting W first and V second would give me the opposite of the area that I got here, giving me a negative area. So when a determinant comes out negative, you can take its absolute value, and the absolute value will still correspond to the area of that parallelogram. But the fact that it's negative simply means that these vectors had an opposite orientation. The first column would have to be, to get from the first column to the second, you'd have to be going clockwise in the case of a negative determinant. And we can interpret that in a certain sense as a linear transformation flipping space over. I'm not going to build too heavily on that concept because it helps if I have some animations, which I don't have. But okay, now let's continue working with the idea of a determinant being. Actually, I'm sorry. Let me. I addressed positive and negative determinants. I didn't say what it means for a determinant to be 0. What if your determinant is equal to 0? Well, we know in the case of a 2 by 2 matrix, if your determinant is 0, that would mean that your columns are scalar multiples of each other. But what does that look like geometrically? Well, here, these two vectors, v and w, were not scalar multiples of each other, because if they were, they would have to be parallel. But if you take two vectors that are parallel, look at what do you think happens to this parallelogram? These vectors will squish it down to a line, which has no area. So a determinant of 0 is exactly what you would expect. It's something that has 0 area. Okay? All right. I think I'm just about out of time on this video. I think I'm going to make a part 3 where I'm going to cover the rest of this. So we're going to go ahead and leave that here.